Hello everyone. Today's topic is angular momentum. What is a rigid body? A rigid body is an object whose size and shape do not change. What is angular momentum? Angular momentum is the rotation. What momentum is to linear motion, which means angular momentum is to rotation what linear momentum is to linear motion. Angular momentum is an object's tendency to keep rotating. It is denoted by L and is a vector pointing along the rotation axis. So if the object is rotating about x-axis, then the angular momentum is pointing in the direction of x-axis. If it is rotating about z-axis, then the angular momentum is in the direction of x-axis. Angular momentum of an object rotating about a fixed point is the product of the object's moment of inertia and its angular velocity. It is denoted by L, and it is measured as the product of the moment of inertia and angular velocity. It is measured in kg, meter squared per second. Of course, it is a vector quantity. So where in the formula, L represents the angular momentum, which is measured in kilograms meter squared per second. Then I represent the moment of inertia, which is measured in kg meter squared. Then omega here represents the angular velocity, which is measured in radians per second. So for a conserved rotational motion, then the mechanical energy of the rotating object includes its rotational kinetic energy, which is given by half I omega squared. So angular momentum is conserved for an isolated system. An isolated system is a system where the net force is zero, or the net external force is zero. Let's consider this example here. A new way of multiplying two vectors is introduced in this chapter. What is it called? Is it a dot product? Is it a scalar product, tensor product, cross product, or the angular product? And of course, it is a cross product. So you'll see more about it later on. So a rigid body is an extended object whose size and shape do not change as it moves. Particle-like atoms are held together by rigid massless rods. A rigid body cannot be stretched, compressed, or deformed. All points on the body have the same angular velocity and angular acceleration. Okay, so we have an object here which is rotating about parabolic trajectory. The figure below shows how the velocity vectors at the top, center, and bottom of a rolling wheel are found. So the point of the bottom of a rolling object is instantaneously at rest. So you can see translation plus rotation, which is rolling. One-dimensional motion uses a scalar velocity and a force F. A more general understanding of motion requires vectors, speed, and a force. Similarly, a more general description of rotational motion requires us to replace the scalars omega and tau with the vector quantities omega and tau, or omega and tau. Doing so will lead us to the concept of angular momentum. So the magnitude of the angular velocity vector is omega. So the angular velocity vector points along the axis of rotation in the direction given by the right-hand rule as illustrated. Okay. So where these fingers, curl along the rotational axis like this. then that will be the direction is of angular velocity, which is the same as the direction of angular momentum. The dot product is one way to multiply two vectors, giving a scalar. Then another way of multiplying two vectors, but giving now a vector, is what it is a cross product. So if vectors A and B have angle between them, which is alpha, then their cross product is a vector. So a vector A cross a vector B, the magnitude is the same as AB sine alpha, where alpha is the angle between the vectors. So the cross product is perpendicular to the plane of vector A and vector B. The right-hand rule for the direction comes in several forms. Try them all to see which works best for you. Okay, so you can use this right-hand rule where the thumb represents the direction of A, then the pointing finger represents the direction of B. Then the cross product vector is represented by the middle finger. Okay. So let's note that the cross product of B and A is different from A cross product B. And the cross product of B cross A is actually negative A cross B. Okay, let's consider this example here, where E is the cross product of C and D. So we have D here, which is pointing upwards, and we also have C, which is pointing 20 degrees below the negative x-axis. So we need to calculate E here. So sometimes the vectors are denoted by bold. We bold the letters to represent or to show that they are vector quantities, or we put a cap on top of them. Either you put a cap or you bold them. So in this question, E is bolded, C and D. It shows that E, C, and D, they are all vectors. Okay, so D here is 1 meter. Upwards, then C is 2 meters. So the solution, we have C, which is 2 meters, D is 1 meter. So theta is going to be 90 degrees plus 20, where 90 degrees is the angle between D and the negative x-axis. And when we add 90 and 20, then we get 110 degrees. Then let's consider the formula. Of course, C cross D is the same as CT sine of theta. Then we substitute the known values. C is 2 meters, D is 1 meters. Then angle theta is 110 degrees, which is the angle between C and D. So then the answer is 1,88 meters squared. So if we use the right-hand rule, we realize that it is into the page. Okay. So the tag vector, we earlier defined tag as RF sine of phi, where R and F are the magnitudes of the vectors. So this is a really cross product. Where tau is equal to R cross F. The particle of mass m is moving. The particle's momentum vector makes an angle beta with a position vector. So you can see P here represent the linear momentum, and the mass m and the speed v. Okay, and the distance r. So we have x YZ plane here. Then on the other side, then we have linear momentum, which is R, cross product of P, where P is linear momentum. Then we know that P is the same as mv. Then if we substitute, so we have L, which is Rp, sine of theta or sine of beta, where beta is the angle between R and P. Then now we substitute now P with mv, then we get angular momentum, which is equal to mRV sine beta. So why this definition? Then angular momentum is equivalent to R cross P. If you take the time derivative of L and use the definition of the torque vector, then you find that the derivative of angular momentum with respect to time is the same as the net tau, or the sum of the torque. Torque causes a particle's angular momentum to change. This is the rotational equivalent of the rate of change of momentum, which is the same as the net force, and is general statement of Newton's second law for rotation. So okay, now the proof of this equation, the net torque is equal to the rate of change of angular momentum. We can prove it as follows. So we know that the angular momentum L is the same as R cross V. So now if we derive both sides, we have dl, okay, actually this is dl dt. We have dl dt, this is t, which is equal to m ddt, then the product of R cross V. Then if we use the product rule here, then we have m, first we derive V, then after that we derive R. Then we get this, we know that the rate of change of velocity is acceleration, which is A, and the rate of change of R is V. This is what you get, that we get M R cross A, which is equal to RMA, so which is equal to R cross F net, which is the same as the net torque. So we've managed to prove that formula. Okay, this is the tutorial problem that you need to do it at home. A particle moves in the XY plane in a circular path of a radius R, as shown in the figure below. Okay, let's consider the question. Determine the expression for the magnitude and direction of its angular momentum relative to the origin when its linear velocity is v. Okay, angular momentum of a rigid body. For a rigid body, we can add the angular momentum of all the particles forming the object. If the object rotates, for example, on a fixed point or on a fixed axis of symmetry, then it can be shown that the angular momentum is equal to the moment of inertia times the angular velocity. And we know that the rate of change of angular momentum is the same as the net torque. That is Newton's second law. Okay. So now if the system is isolated, then the rate of change of angular momentum remains the same, which means the net torque is equal to 0. Then which means the angular momentum is constant. Then we have a law of conservation of angular momentum, which states that the angular momentum L of an isolated system is conserved, which means that the final angular momentum is equal to the initial angular momentum. So which is conserved for both the magnitude and the direction. So let's consider here a skater spins. The external torque is small, so her angular momentum is almost constant. By drawing in her arms, the skater reduces her moment of inertia. To conserve angular momentum, her angular speed must increase. Okay, let's consider example number 4 here. A 20 centimeter diameter with 2,0 kg solid disk is rotating at 200 revolutions per minute. A 20 centimeter diameter 1,0 kg circular loop is dropped straight down onto the rotating disk. Friction causes the loop to accelerate until it is riding on the disk. What is the final angular velocity of the combined system? Okay, so we have the disk rotating, so the loop is dropped, and initially the loop is not rotating. Then, okay, the disk here is rotating at the initial speed of 200 revolutions per minute. Then now we have the system here, which is rotating at the final angular velocity. Okay, so the friction between the two objects creates tugs that speed up the loop and slow down the disk until they move with the same speed. But these tugs are internal to the combined disk plus loop system. So the net tug is equal to 0, and the total angular momentum of the disk plus loop is conserved. Okay, so we have that system there. Let's consider the solution together. So we know that the angular momentum is conserved, which means the final angular momentum is equal to the initial angular momentum. So we know that the angular momentum is given as the product of the moment of inertia with the angular velocity. So which means we're going to have the moment of inertia of the disk times the angular velocity plus the moment of inertia of the loop times the angular velocity final, because both the disk and the loop are rotating. So they both have the angular momentum. But initially, we only have the angular momentum of the disk because the loop is not rotating. So we have, just like in a linear motion, if the object is not moving, that object does not have a linear momentum. So initially we have the angular momentum of the disk, which is the product of the moment of inertia of the disk times the angular velocity. Okay, so now we make the final angular velocity the subject of the formula. So we have this expression, then we substitute the known values. We know that the initial angular velocity is 200 revolutions per minute. Then we can calculate the moment of inertia of the disk, which is half mr squared, where m represents the mass and r the radius. So we get 0.01 kg meter squared. Then we calculate also the moment of inertia of the loop, which is mr squared, according to the formula, which is given as 0.01 kg meter per second. Kg meter squared, then we substitute to the formula, then we punch the calculator, we get the answer. Okay, another example, 2 buckets spin around in a horizontal cycle on frictionless bearing. Suddenly it starts to rain as a result. Okay, let's choose here the appropriate answer or the most correct answer. So the A says the buckets speed up because the potential energy of the rain is transformed into kinetic energy. B, the buckets continue to rotate at constant angular velocity because the rain is falling vertically while the buckets move in a horizontal plane. Okay, both A and B are wrong. C, the buckets slow down because the angular momentum of the bucket plus the rain system is conserved. That is correct. So this is the same as the previous example of the disk and the loop. Okay, C is the correct answer. Okay, consider a procession of a gyroscope. So consider horizontal gyroscope with the disk spinning in a vertical plane that is supported at only one end of its axle point of rotation as shown. We'll expect it to simply fall over, but it doesn't. Okay, instead, the axle remains horizontal, parallel to the ground. while the entire gyroscope slowly rotates in a horizontal plane. This steady change in the orientation of the rotation axis is called precession. And we say that the gyroscope precesses about its point of support. The precession frequency now is much less than that disk rotational frequency, which is omega. Shown in a non-spinning gyroscope, when it is released, the net torque is entirely gravitational torque. Initially, the angular momentum is 0. Gravity acts to increase the angular momentum gradually in the direction of the torque, which is the I direction. This causes the gyroscope to rotate around X and 4. Okay. Shown is a gyroscope initially spinning around the x-axis. Initially, gravity acts to increase the angular momentum slightly in the direction of the torque, which is in that direction. This causes the gyroscope angular momentum to shift slightly in the horizontal plane. Gravitational torque vector is always perpendicular to the axis, so PL, or the point of rotation. So TL is always perpendicular to L. Like the change of L is always perpendicular to L for small change. Okay, let's consider the tutorial problem number 2. You need to do it by yourself at home. Calculate the magnitude of the angular momentum of a bowling ball spinning at 10 revolutions per second. The mass of the ball is 6,0 kg with a diameter of 24 centimeters. Okay, this is how, so the rotation, this shows the rotation. Here we have x-axis, then y-axis, and x-axis. So the direction of angular momentum is along the positive x-axis. Tutorial problem number 3, you need to do it also by yourself. A star rotates a period of 30 days about an axis through its center. After the star undergoes, so in other words, a star rotates a period of 30 days about an axis through its center. After the star undergoes a supernova explosion, the stellar core, which had a radius of 1,0 exponent 4 kilometers, collapses into a neutron star of radius 3 kilometers. Now you need to determine the period of rotation of the neutron. Okay, that is the end of the lesson. Thank you for taking part in the lesson. All the best.